Reducing overfitting can be achieved by regularizing the model, which essentially means imposing constraints on the model to reduce its degrees of freedom. So it makes it harder for the model to overfit data, right? So we want to ensure or make our model harder to overfit. So one effective way to regularize a polynomial model is by reducing the degrees of the polynomial, right? So that makes sense. Regularization of a linear model typically involves applying constraints to the model coefficients, which leads us to the question, how is regularization implemented mathematically, right? So what is the math for regularization? I want to talk a little bit about the word regularization. What we're trying to do is develop models that can fit a number of different data sets, right? So that's what we mean by a regularization of the model, right? We don't want a special model for every data set. We want one model that can fit a number of data sets. And to do that, we want to make sure our model doesn't overfit. And so that's what we're looking at now. So a common algorithm for this is called ridge regression. 2.7.1, that's ridge regression. And ridge regression modifies linear regression by adding regularization terms to the cost function, which compels the learning algorithm to fit the data while keeping the model weights as small as possible. So it's important to note that it's only during so let's say regularization terms are only applied during training phases. Right, so during the model performance phase, the on-regularized model is used. So what does that look like for our equation, right? So we are going to take J, which is our cost function of our parameters theta. Again, we can also write that as MSE because we are using mean squared error so far. But you could use other error functions. That's what the J is for, of theta is equal to alpha 1/2 the summation of I equals 1 theta I squared of n. So the hyperparameter, right? The hyperparameter alpha dictates the degrees of regularization. Dictates the degrees of regularization, right? So if, oh, sorry, this equation is wrong. That is not equals, that is plus. So if alpha is equal to 0, then the entire second term falls off. And this just regresses back to linear regression. If alpha is very high, the model weights are significantly shrunk, resulting in a nearly flat line through the means of the data. So the bias term is not regularized as indicated in the summation that I here starts at 1. So let's do it. Let's do that in blue. So as I starts at 1, bias not affected. Right, and because our bias isn't affected, so for like our linear model, that would be the y-intercept. So let's look, I think the best way to do this is probably just to look at some plots of ridge regression. And so this is what ridge regression looks like. Hopefully, maybe if it's a bit bigger, but okay. So we can have a ridge regression is just adding of constraints. So we can regularize our model. We can have linear ridge regression and we can have polynomial ridge regression. Linear ridge regression doesn't make too much sense because a linear line, isn't actually at a huge risk of overfitting, which makes sense. But in a little ways that you could see, if you think about it mathematically, a horizontal line is less overfit than a line that has some sort of angle to it, right? And so the ridge regression, the higher we put alpha, the more generalized our model is. It makes more sense in a polynomial, right? So in a polynomial, you can get these blue lines here, the blue and the orange lines. You can see that the blue line, except for that jagged jump, tries to cut through and pick up some of the data, particularly here around 1.5. But if you were to look at just the orange line, right? The orange line has a more conservative model of that data. It's not as affected as much by this outlier. And then the green line has a much more conservative model of the data in general until it comes up here and hits the end of your data set. But you always have issues with polynomials at the end of data sets. So that's what ridge regression allows. So when we do this in sklearn, let's talk about the process of doing this in sklearn. So in sklearn, the data is expanded using polynomial features. Which is then scaled. And finally, ridge regression is applied. So what's interesting about ridge regression is actually there is a closed form solution, right? So ridge regression can be performed using a closed form solution or through gradient descent, just like linear regression. The pros and cons for each method are the same as before. If you want the closed form solution, for ridge regression, it is theta hat is equal to x transpose times x plus alpha capital A, that whole term inverse, and that inverse is what slows down the closed form solution, right? And that's what makes it quite hard to do with large data sets, times x transpose times y. Where alpha influences the regularization, right, as before, and A is a n by n identity matrix. With 0 in the top left.